All right, everybody, welcome to our next lecture. So, today we're going to cover quantitative data analysis basics for environmental justice and social science research. Okay, so um, don't turn this video off yet. All right, bear with me. I'm going to give you a very, very high level overview of how to use descriptive statistics and conduct some hypothesis testing. Now, I know that statistics terrifies some of you. It used to terrify me and still does some days, but um, I'm I want you to stick with me, okay? I'm gonna make this as non-boring, non-mathematical, and as easy to understand as possible, right? I'm going to show you that statistics are a powerful tool for measuring and documenting evidence of injustice, making arguments that courts, governments, and corporations cannot easily dismiss. They have to take seriously. And I really want to show you that a well executed statistical analysis can provide evidence that can change policy, right? Let's make this useful, okay? So, in this whirlwind here of statistics. Again, this is not a statistics course, but I'm gonna do my best here. But I want you to understand why quantitative methods matter for EJ research and social science, specifically what they can and cannot do. Right. Second, I want you to be able to calculate and interpret descriptive statistics for EJ data. I want you to be able to use these as a baseline and to be able to communicate effectively in data. Okay. I want you to actually understand what the numbers mean to the best of my ability. Again, dive deeper into stats courses to really unearth that. But I want you to really understand the analyses you're conducting, not just the software you're using, right? Third, I want you to grasp when and how to use hypothesis testing specifically to support and answer your research questions. And I want you to be able to identify statistical tests for different types of questions, right? So in your project, your research proposals, if you're going to propose conducting some analyses, I want you to be able to explain why, right, to justify that. And again, I want to discuss power and recognize the limitations and political dimensions of data, of quantitative analysis, and how, again, numbers are also non neutral. And then I'm going to give you sort of a cheat sheet, a high level, 30,000 foot basic statistical thinking to real world problems idea. Okay. So, why even bother with quantitative methods, right? You might be like, I cannot wait to never use numbers again. I felt the same way at many points of my life. But numbers provide specific forms of evidence that other methods just cannot. Okay. Quantitative methods, they quantify the magnitude of disparities, which is really important, right? Not just pollution is worse here, but pollution is 3.2 times higher in this specific community. We had to arrive at that number, right? They test whether patterns are systematic or could have occurred randomly, right? They really enable at their core, comparison across groups, places, and time periods, which we've emphasized is incredibly important in this type of research. They have the power to track change and show whether conditions improve or deteriorate, right? For monitoring and evaluation, reporting, we need those to be quantifiable. And they have another power of making predictions about future conditions, right? You can model, you can project, you can test the reliability or the predictability of something, air pollution, runoff, agricultural waste. And critically, they provide, what is the bedrock of legally admissible evidence for litigation, right? You're going to be asked to report numbers throughout your life in your professional research, practitioner-based career, right? Numbers, again, they don't speak for themselves. You might have heard that, but I disagree, right? They answer questions we ask. If you ask whether Black neighborhoods have higher pollution exposure than white neighborhoods, statistics can answer that, right? But if you ask why those disparities exist, statistics alone can't answer that, right? So we need different tools for different questions. So what can't quant do? So before we dive into techniques, I want to acknowledge that, quantitative methods, they can't capture lived experience. Okay. A regression coefficient cannot convey what it feels like to watch a child struggle to breathe because of local pollution. Quantitative methods cannot explain fully why patterns exist, right? They describe patterns, but require theory and additional investigation to explain causation. They cannot replace community knowledge. Communities know their own experiences and needs better than any data set. Quantitative analysis can sometimes also obscure individual variation by focusing on averages and aggregates, okay? Numbers can also be weaponized to delay action. We need to do more research. We need to get more data. This can become an excuse for inaction. So we need to balance, right? We need to use quantitative methods alongside qualitative approaches that you learned earlier in the modules, right? Interviews will reveal the mechanisms, statistics will reveal the patterns, and provide additional evidence to support our claims, okay? Together, that mixed methods is very powerful. So let's start with descriptive statistics, right? These summarize characteristics of your data. There are two main categories, right? You have first measures of central tendency. This answers like what's typical in your data, okay? The mean is the average, add all values and divide by the count. The median is the middle value when data are ordered. The mode is the most common value, right? We learned these throughout our education, but you're going to need to report these in your data, right? These are important numbers to understand. Second, we're going to look at measures of dispersion, right? How spread out the data are. Range is your minimum to maximum, right? Standard deviation is the average distance from the mean, right? From the average. Interquartile range is the middle 50% of your data. You need both. Central tendency tells you what's typical. Dispersion tells you how much variation exists. Okay, you need both of these. You need to report both of these. Two communities might have the same average pollution exposure, but very different variation in that exposure, right? Which matters for health impacts. We have to be able to understand that difference and be able to unpack these data and look at them in different frames and lenses, right? To really get to the bottom of what's going on. Now, mean versus median matters particularly in EJ research because our data are often skewed. Okay. So, an example would be blood lead levels in 100 children measured in micrograms per deciliter. It's above my head, too, right? 95 children, let's say, have levels between 1 and 3. 5 children have extremely high levels between 45 and 60. So, now we need to calculate the mean, right? Calculate the median, and then which tells the truth? Well, both. Different truths, right? The mean is showing the total burden, averaging in those extremely high exposures. But the median shows typical exposure, what a randomly selected child likely experiences. For skewed environmental justice data, we should report both, right? The mean is showing us the outliers and total burden. The median is showing typical conditions. This makes for a powerful comparison and a powerful story through data. Okay? And why does standard deviation matter? Well, consider air pollution exposure in two neighborhoods, right? PM 2.5 parts per million measured under 2.5. Can't remember what the measurement bit is, but it's the pollutants, okay? Oh, wait, gram. I don't know. Anyway, measured in micrograms per cubic meter. That's what it is. Neighborhood A has a mean of 25 and standard deviation of 2. Okay. Everyone in this neighborhood experiences similar exposure. The data shows that it might be predictable. It is predictable. But neighborhood B has a mean of 25 and a standard deviation of 15. This is wide variation. Some days exposure is 10, some days 40, right? Same mean, completely different risk profiles. High variability means unpredictability, okay? Residents cannot plan around exposure. Health impacts may be worse with high variability, even at the same average levels. So standard deviation is not just a technical detail. It's meaningful for understanding real environmental impacts and planning accordingly. And distribution, again, can tell stories as well, right? And this is really important in when we're doing environmental justice research because we can tell stories about underlying processes, okay? So a normal distribution is the symmetric bell curve, right? You've seen this, right? Just goes up and comes down. Many natural phenomena follow this. And importantly, many statistical tests will assume normal distributions, okay? But a skewed distribution has a long tail on one side. Right skewed means a few very high values are pulling the mean up. Okay. Income data are often right skewed, right? A very few wealthy people pull the average up. Pollution exposure data are often right skewed. Most days are moderate, but some days have extreme spikes. Okay. But a bimodal distribution has two peaks. This may indicate two distinct groups in your data, right? Always visualize your data before you conduct analysis so you can see these trends, right? A histogram or density plot is going to reveal whether assumptions of statistical tests are met. If your data are highly skewed, certain tests may be inappropriate, right? So again, this is incredibly high level. You need to be able to understand and visualize this and see these trends to help guide you in conducting accurate analysis. So an example would be, let's say, in a city, monthly household income across 50 districts in 2022, the mean was measured at $38,400. The median is $32,100 and the standard deviation is $18,200. Okay. What does this tell us, right? Well, it may indicate and it will show that the data are right skewed, meaning the mean exceeds the median. Some high income districts are pulling the mean up. The median will better represent a typical household because it's not affected by those extreme values. Do you understand? High standard deviation indicates substantial inequality across these different districts. Some districts have much higher income than others. And this matters for targeting interventions, right? If you use the mean to define low income, you'll miss many struggling households. If you use the median or calculate the district specific thresholds, you may target more accurately, right? Descriptive statistics can guide this design and decision making. So moving from description to comparison, a central question in this field is do, a specific percentage, like low income communities, let's say, are a variable, a socio-demographic variable in a community face higher exposure than another group, right? So in this example, do low income communities face higher pollution exposure? The approach is to compare exposure between the groups, right? Going back to many lessons we've talked about throughout the semester, right? Calculate mean exposure first for each group, right? Test if the difference is statistically significant. Then consider practical significance, right? This is also called effect size. Statistical significance means the difference is unlikely due to chance, okay? Practical significance means the difference is large enough to matter for health, well being, or making serious policy recommendations, serious changes, right? Again, you need both. You need that statistical significance and the practical significance, okay? A tiny difference, it might be statistically significant with a large sample, but in practical significance, it's meaningless, right? So a large difference might not reach significant significance with a small sample, but it still matters, right? We have to think about this from multiple approaches, multiple lenses of analysis. Hypothesis testing logic works like this, right? You start with the null hypothesis. This is symbolized at H0. This typically states no difference between groups, right? The alternative hypothesis, H1, states there is a difference. The process is to calculate a test statistic from your data, right? Determine the probability, the p-value, of observing this result in the null hypothesis if the null hypothesis were actually true, okay? If p is less than 0.05, that's the conventional threshold. You reject the null hypothesis, right? You conclude the difference is statistically significant, right? So what does the p-value mean? Well, if no real difference existed between groups, you would observe a difference this large or larger by random chance only 5% of the time. It's low probability, so you infer a real difference exists. Again, this logic is backward from how people intuitively think, right? Which is why it's confusing, and I know you're already confused, probably. You're calculating the probability of your data given the null hypothesis, not the probability of the null hypothesis given your data, okay? Again, I'm giving you the most high-level overview of this. There's a lot more to unpack with that, okay? Now we move to t-tests, right? So the independent sample t-test compares means between two groups. When do you use it, right? When you have a continuous outcome variable and two independent groups. For example, compare average distance toxic facilities between two different demographic groups and their neighborhoods, right? The assumptions will matter. You need a continuous outcome variable like distance in meters, right? Groups must be independent, not the same people measured twice. Distributions should be approximately normal, though with large samples, this matters less, right? We'll talk about that in a moment. And groups should have similar variances, right? Similar spread in the data. The output includes a t statistic, which is a standardized difference between these groups. A p-value indicating statistical significance and the actual mean difference in original units, right? You want to always report the mean difference, not just the p-value. People need to know the magnitude, right? So again, you're comparing between two groups with this t-test, right? You're comparing the average distance between white and black neighborhoods to the toxic facility. These are the assumptions. Your output will give you some guidance on how to report what you're observing. Chi-square test, okay? So, well, let me go back to t-test, right? Let's give an example because that was a bit heady, right? So let's talk about Louisiana Cancer Alley, right, as an example. So if we want to ask the question, do predominantly black census tracts have higher toxic air emissions than predominantly white tracts?